Hello. In this video we're going to talk about vectors and how to go about writing them and describing them in terms of its components and in terms of a magnitude and angle. And vectors are a kind of variable that are talked about extensively in physics, and you'll also encounter them at the end of trigonometry. So to start out, when you're doing math, most of the variables you've been talking about have been scalars, which are variables that only have magnitude or only have a single number associated with them. They can have units attached, but it's just a single value. So like the time is 50 seconds, or you have a mass of 2 grams. Instead, vectors are variables that have multiple components or multiple numbers associated with them, and you'll also see them described as having magnitude and direction. But the key piece to note is that you have multiple numbers, multiple pieces of information going on with them. And when you look at most textbooks, you'll see vectors notated in boldface type, which if you're writing on paper or writing on the board, it's really hard to tell. So you'll also see the arrow sign used on top of the variable as well. So vectors, they have multiple components with them, and they're noted in either bold or with the arrow sign on top of the symbol. So first we'll look at vectors in terms of their components. And when we talk about the vector components, we need to have a unit system or a coordinate system associated with them. And keep things easy, we'll look at the linear or Cartesian coordinates where everything is a straight line. You have the x direction going horizontally, the y direction going vertically, and the z direction, you could say, is coming out of the screen or into the screen, out of the board into the board, or out of the paper into the paper. And those x, y, z directions you'll also see written as I, J, K. I tend not to use that because it's hard to distinguish the I and the J a lot of times. And when you want to signify a given direction, you put a caret sign on top of the variable. So for example, x with the caret on top means the x direction, y or j with a caret on top means the y direction, and z or k with a caret on it means the z direction. And these are called unit vectors. They're vectors that just have a length of 1 and are there to signify direction. So we'll use these unit vectors to describe the components of a vector. So let's say we have a vector A. Again, we'll signify it either in boldface or with an arrow on top of the variable. And the most fundamental way you can describe a vector is in terms of its components. And you'll see a few different conventions used. When you want to specify a given component of a vector, you use a subscript. So for example, the x component of A is A subscript x, and the y component of A is A subscript y, and the z component of A is A subscript z. So one way you'll see a vector written is in this bracket notation, where you have brackets and then each component separated by a comma. Or you could see this written in long form, which is the x component of A in the x direction plus the y component of A in the y direction plus the z component of A in the z direction. Again, when you manipulate vectors, writing it in terms of its components like this is the most fundamental way of doing so. But let's say we want to look at a vector in terms of its magnitude and angle. Well, the magnitude of a vector you can find by doing an extension of the Pythagorean theorem. And you'll see the magnitude of a vector, either the vector with the bars around it like the absolute value sign, or you'll see just the vector in normal face without an arrow. Both of these mean the magnitude. But if you want to just make it clear to yourself, I would encourage you to use the absolute value sign here. And again, it's an extension of the Pythagorean theorem where you do the x part of the vector squared plus the y part of the vector squared plus the z part of the vector squared, all under the square root. Now, when you look at the angle describing a vector, if you have a vector in 3 dimensions like you have here, you actually need 2 angles to describe the vector. To make things simple, we'll look at just a 2-dimensional case. So here I have this vector A, it's going to the right and up, and we're going to look at its magnitude and an angle to describe it. Here, because we're dealing with a secondary form, we're not necessarily talking about a vector directly in terms of its components. We have to be a little careful, because when you assign an angle to a vector, you always have to specify where that angle is located, because depending on where you locate the angle, it's going to change the values of your sine, cosine, and tangent. And the way you can keep this straight is by always using the base definition of those trig identities. So sine is always defined as the opposite side of an angle divided by the hypotenuse of the triangle. Cosine is always defined as the adjacent side to the angle divided by the hypotenuse, and tangent is always defined as the opposite side of the angle divided by the adjacent side of the angle. That being said, most often you're going to see the vector described with an angle with respect to the x-axis. So for this particular angle, or vector A, drawn this red angle theta above the plus x-axis, and you want to specify that it's above the plus x-axis here because you want to avoid any ambiguity. You want the reader to understand where exactly the angle is located so they know where the vector is pointing. And so we have an x component of the vector, we have a y component of the vector, and you can use your Pythagorean theorem to get the magnitude of the vector. And here we'll apply our trig identities to say find the x and y components of the vector given the angle, or we can find the angle given the x and y parts. And when you do this, you always want to fall back to the base definitions of these trig identities. So for example, we want to do the sine of this angle. Well, sine is always defined as the opposite side of the angle over the hypotenuse. So for this red angle theta, the opposite side of that angle is the y component of A, and the hypotenuse is the magnitude of the vector. So sine of theta, sine is always opposite over hypotenuse, and the opposite side of this red angle is the y component of A, and the hypotenuse is the magnitude. Likewise, cosine here, cosine is always defined as the adjacent side over the hypotenuse. So when we look at this red angle theta, the adjacent side of it is the x component of A, and the hypotenuse is still the magnitude. So cosine of this theta, adjacent over hypotenuse, is ax over magnitude of A. Then lastly, tangent is always defined as opposite over adjacent. So for this red angle theta, the opposite side of it is the y component of A, and the adjacent is the x component of A. So again, tangent is always opposite over adjacent for this red angle. The opposite side is the y component of A, and the adjacent is the x component of A. Again, most of the time you'll see the angle or the vector described with the angle with respect to the x-axis, but this isn't always the case. Sometimes you'll have the angle described with respect to the y-axis. So I've drawn this yellow angle, or phi, with respect to the y-axis, and we have the same x and y components of before, same magnitude as well, but now we have to be a little careful as to what our trig values are. And when we write this out, we say our vector A has a magnitude and it's at an angle of phi, and we specify that it's right of the plus x or plus y axis, again to avoid any ambiguity as to where this vector and angle are located. So let's do our sine. Sine is always defined as opposite over hypotenuse. So in this case, the opposite side of this yellow angle phi is the x component of A, and the hypotenuse is still the magnitude. And likewise, the cosine, which is always defined as the adjacent over the hypotenuse, the adjacent side of this yellow angle is the y component of A, hypotenuse is still the magnitude, and tangent would be opposite, which is AX, over adjacent, AY. So this is giving you the reverse of what you had before when you had the angle with respect to X. And so to avoid any confusion, you can always rely on the base definitions of your trig identities, because those are fundamental. The specific values of them are going to be different based on what angle you're talking about. You'll have different values if you're talking about this angle with respect to the x-axis versus this angle with respect to the y-axis. And again, if you're given the angle in the magnitude, you can multiply both sides by the magnitude to get the x and y components of the vector. So to sum up, when you talk about a 2D vector in terms of its magnitude and angle, you always want to specify what that angle is with respect to an axis, because you want to avoid any ambiguity for the reader, and depending on where you draw the angle, the values for your sine, cosine, and tangent are going to be different. But no matter what, you can always rely on your base definitions of sine, cosine, and tangent to do those computations to figure out the x and y components of the vector and to figure out those specific angles. So I hope you found this video helpful. I'll be posting another video soon on manipulating multiple vectors, so adding and subtracting and multiplying them.